All right. Let's talk about ionic bonds. So there's three types of bonds, and the one that we're going to start with is ionic bonds because we now have learned how to make dot structures and we know about ions. I'm just going to do a quick reminder about how ions work here. And then we're going to start talking about how ionic bonds can form. And the key here is that ionic bonds are between metals and non-metals. Okay. So if you've got metals and you've got non-metals, they can bond through ionic bonding. Okay. And I'm going to show you what that is right now. So if we look at our periodic table here, the metals, right? That's everything that's in color right here. So all this stuff on the left side of this kind of stair step, these are the stair steps right here, the metalloids, which we're going to just use them as stair steps for now. Everything on the left of that stair step here is going to be able to bond with everything on the right of that stair step using this method, ionic bonding. Okay. There are a couple of exceptions, like hydrogen and carbon do weird stuff. So, but we'll come back to those later. All right. So, to start, let's talk about ions, right? So, remember that we've got things like, wow, everything in column one, like lithium, is going to have one valence electron, right? Like this. And then over here, everything in column eight, like fluorine, is going to have seven valence electrons. One, two, three, four, five, six, seven, right? Okay. So here's the deal. What every atom wants in order to become an ion is for it to get a full outer shell, right? So things like the noble gases have a full outer shell. Helium's got two electrons, it's happy. Neon has eight electrons in its valence, it has eight, and eight makes it happy, right? So things are seeking a full outer shell. So lithium is actually seeking to lose its electron, fluorine is seeking to gain its electron, right? Okay, so similarly with beryllium, beryllium has got two valence electrons, one, two, okay? I'm just going to do the whole row. Boron, carbon, nitrogen, oxygen. Okay. Boron has one, two, three. Carbon has one, two, three, four. Nitrogen has five. Wow. I made nitrogen oxygen. Oxygen has six. One, two, three, four, five, six. There we go. Okay. So these things are either going to want to gain or lose electrons, right? So here's where we draw the line. Right right here, straight through carbon. So everything to this side is going to want to lose, and everything to this side is going to want to gain, right? Because it's easier to do what is going to cause you to have to use less electrons, right? So I'm going to delete that for now. I'm just going to delete carbon for now. Okay, here we go. Okay, so we know that lithium wants to lose one, beryllium wants to lose two, and boron wants to lose three electrons. So what kind of ion are these things going to form? Everything in the first column is going to form a 1 plus ion. Everything in the second column is going to form a 2 plus ion. And then everything over here is in number three is going to form a 3 plus ion. And we'll talk, okay, why are these positive, right? So the reason they're positive is because when you lose this electron right here, you now have one fewer electron because you have more protons than electrons in the atom overall. So by how many? By one. So it's one positive charge. When you lose two electrons, right? You now have two fewer electrons than protons, so the overall net charge of the atom is two positive. Similarly, when you lose three, one, two, three, your net charge is three positive. Okay. Now, over here on the right side, we are looking to gain electrons, right? So we want to make a full outer shell, right? So nitrogen needs to gain one, two, three electrons. So it will have a three minus charge. Oxygen needs to gain one, two. So its ion will have a 2 minus charge, and fluorine just needs to gain 1. So everything in this column is going to have a 1 minus charge, okay? Because remember, when you add electrons, you're adding negative charges, okay? So this is true for the things in this column for when we're doing bonds, right? So when you make these ions, they need to lose or gain this many electrons to be happy, to have a full complement, to have a full outer shell, okay? So that's the case for all of this stuff. So everything in the first column, right, is 1 plus. Then we've got 2 plus, we've got 3 plus, we've got 3 minus, 2 minus, 1 minus. So hopefully you see that pattern and it's very easy for you to understand. Okay, so let's do our first example. Our first example is going to be using sodium, which is a 1, right? And chlorine, which is a column 17. So let's just jump into that really quick. Here we've got sodium over here, and here we've got chlorine over here. Okay, so let's do the Bohr model for sodium, which I know we don't really need to do this very much. Actually, you know what? Do we need to do this? I don't think we need to do this. So let's just do the sodium dot structure. So sodium's got one valence electron. Okay. So we draw Na like this. So let's use a different color. Sodium with one electron. And chlorine is in the last row, or the last column rather. So chlorine's going to have seven valence electrons, right? So one, two, three, four, five, six, seven. I know this is going to bother somebody, so I'll just take it away. There we go. Okay, so here's the deal. Sodium, in order to be happy, needs to ditch this electron. Chlorine, in order to be happy, needs to gain the electron. So what happens is sodium is like, here you go, chlorine, have my electron. So sodium loses its electron. Chlorine gains an electron. What did we do? We made sodium plus by losing an electron, and we made chlorine minus by gaining an electron, right? So now we've got these two particles. We've got sodium and we've got chlorine, NaCl. And then Na has a positive charge and the Cl has a negative charge. And we know that positive and negative are attracted to one another, right? So because of the electrostatic difference in charge, these two particles are now attracted to one another. This is called an ionic bond. So our first ionic bond that we've made is NaCl. You might be familiar with NaCl as table salt. And now the only trick is we have to figure out how to name this thing, right? So you know that sodium is a metal and that chlorine is a non-metal. So if sodium is a metal, I'll use a different color for chlorine here. Green. And chlorine is a non-metal. Okay. The way you write these formulas is always the metal comes first, and the metal is always going to be a cation. Wow. Let's use a different color. Use blue for that. So the metal is always going to be the cation, and then the non-metal is always going to be the anion. Okay, remember cation for positive because cats have paws, and then anions are a negative ion, right? So non-metals are always going to form an anion, and metals are always going to form a cation in this case, right? So cation always comes first, anion always comes second. So in this case, metal always comes first, non-metal always comes second. How do we name it? Well, it's very easy for the metal. The metal, you just write the name. So sodium. Done. Now, let's take a look at chlorine over here. So when we had chlorine as a regular old atom, the ending was ine, right? So chlorine. And I'm actually going to write it like this so that you can see what I'm talking about. So we used to have this ending, right? Now, when we write it for the ion, when you make an ion of chlorine, right, Cl minus, you're going to end up with something called chloride. Okay. You're going to use the ending "ide." And this is true for all nonmetals when you make them ions, even if they're 3 minus, it doesn't matter. It's going to be "ide." Okay. So, how do we name NaCl? Sodium chloride. Okay. So, that's our first and our easiest example of how to make an ionic compound. Okay. So, let's get weird with this. Okay. Let's get weird with this. Let's take a look at magnesium and then we'll do fluorine. Okay. So we're going to make what's called magnesium fluoride. And in order to do that, we are going to need to know what magnesium is. So magnesium is here in the 2 plus and fluorine is here in the 1 minus. Okay. So let's mess with this. Okay. So magnesium, wow. Sorry. Magnesium and fluorine, right? Okay. So we've got magnesium, we've got fluorine. We know that if we look at our cheat codes again here, magnesium is going to form 2 plus and fluorine is going to be 1 minus, right? So we've got magnesium and we're going to use blue for this 2 plus, and then we've got fluorine minus. Here's the problem. There's two pluses for magnesium, right? Because magnesium needs to lose. Let's do this because magnesium's got two valence electrons. Magnesium needs to lose two valence electrons, right? And we know that fluorine only has room for one, right? One, two, three, four, five, six, seven. So if magnesium donates one of its electrons to fluorine, what happens to this other one? Well, it can donate it to a whole nother fluorine, right? But only if we have one. So we have to have two fluorines. One, two, three, four, five, six, seven. There we go. And we can make everybody happy in that case, right? So when you see this up here at the top, this is my example, right? So this is kind of the Y down here, and this is the how we show it nomenclature wise. So magnesium donates both its electrons. It loses one to fluorine. It loses another one to another fluorine. So we know we need to have two of these. Okay. So we've got magnesium 2 plus and we've got two fluorines. So how do we write that formula? It's MgF, Mg1, F2, because you need two fluorines to bond with your magnesium. Okay. So overall, that's an error. There we go. Overall, this side has a two positive charge, and this side has a overall two negative charge. So they cancel out and they're happy, right? We don't have to write the charges above these things. We just write MgF2. And what's the name of this? It is magnesium. And then we need our nonmetal fluoride. Okay. Instead of fluorine, it's fluoride. So whenever you do these ionic bonds, you use the "ide" on the non-metal, right? Metal comes first, non-metal comes second because cation anion. Okay, so that's a situation where you might need multiple of these. Okay, so that's a slightly more complicated example. We're gonna do one more, and then we're gonna let you practice. Okay, so our last example here is going to be aluminum and sulfur. Okay, so let's look at our periodic table and figure out where aluminum and sulfur are. Oops, wrong one. Sorry. Okay, aluminum is right here. So we know aluminum is going to have three valence electrons, which means it's going to be 3 plus, right? And we also know that sulfur is right here, which means it's going to be in the 2 minus section, okay, because it has two electrons to gain. And so let's just draw their structures really quick and we'll be on our way. Okay, so aluminum got three, right? And sulfur has got one, two, three, four, five, six. Okay, right? So aluminum's going to be 3 plus and sulfur is going to be 2 minus. So this one is kind of tricky, right? So when we write aluminum, so we need to lose 3 electrons from aluminum, right? So we can lose 2 of these to each sulfur. So if we can lose 2 to each sulfur, one here, one here. That's bad, right? Because we still have one left, don't we? Well, we want to use another sulfur. That's fine, but each sulfur needs 2 electrons from aluminum, right? So if we grab this electron from aluminum, oh no, we only have one. We need another aluminum, don't we? All right, well, here's another aluminum. Let's bop its 3 electrons in there. One, two, three. Okay, great. It can donate one of these to our sulfur. And now that sulfur's happy. And then look, we need another sulfur, don't we? And that sulfur finally is going to be able to take both of these electrons from aluminum, isn't it? There we go. Okay. Now, how many aluminums do we have? Two. How many sulfurs do we have? Three. So let's take a look at our formula. Aluminum, and it's a 3 plus because it's to lose 3 electrons. And we've got sulfur, and it's a 2 minus because it wants to gain 2 electrons, right? The formula that we end up writing is going to be Al2 because we needed 2, S3 because we needed 3, right? Al2, S3 because we needed 2 aluminums and we needed 3 sulfurs. Now, how do we name this? Aluminum, the non-metal, or for the metal rather, and then sulfide because you add that "ide," right, for the ending. Aluminum sulfide. That's it. That's the whole thing. Now, let me show you a cheat code really quick. You see how this is Al3 plus and this is S2 minus? Check it out. Al3 plus, S2 minus. If you always take this number down to the bottom of the other number, you can make the formula. This is a cheat code. I'm not saying that this is how you should understand it, but this is a way that you can pretty much always be right. If you can write these two things as their ions, and then you just take the two ions and you switch the numbers to the other side, and you make it the number of how many of those actual ions there are rather than the actual ionic value, like in terms of electrons, then you'll have the right formula. Okay. It's kind of a little cheat code. It would be nice if you could use this method here where you kind of say, okay, well, how many of these electrons can go here and how many of these electrons can go here? That's the actual way that it works. But once you've done this enough times, you can be like, oh, we just take those two things, make sure one's a metal, one's a non-metal, and we can just flip their numbers and boom, we're mostly there. That works almost every time. Okay. So that's my hardest example that I want to give you for today. Let's do some practice. Come back to this video if you need more help.